Alright, so we are looking at two different examples to help us understand the basics of a hypothesis test. There are two different companies claiming that they can help couples trying to have a baby girl. So company one, Girls R Us, claims that by taking a special pill every day for a month, it'll significantly increase a couple's chance of having a baby girl. In a random sample of 100 couples using the Girls R Us pill, 56 had baby girls, so your p-hat is 0.56. So based on your initial reactions, based solely on the data provided, do you think that the pill from Girls R Us significantly increases a woman's chance of having a baby girl? So the probability of having a girl is 0.5, so if you go from 0.5 to 0.56, but the pill probably didn't add that much value. So probably not in this case. If you flipped it over though and look at the back, we have a different company, so Girls Rock, they're claiming the same thing. So they take your special pill and it'll significantly increase the couple's chance of having the baby girl. So in a sample of 100 couples using the Girls Rock pill, 88 had baby girls, so p-hat is 0.88. So based on initial reactions, so based solely on the data provided, do you think the pill from Girls Rock significantly increases a woman's chance of having a baby girl? So this one, you went from 0.5 to 0.88, so it does seem like something happened here. So the question is, how do you determine that this result is better than that 0.56? Or how do you decide that any result tells you that something significant did happen and it just didn't happen by random luck? So what we do to figure out the answer to that is we conduct a hypothesis test. When we're conducting a hypothesis test, we need to think about what's being claimed because we're going to have to write things out in terms of symbols. So they are claiming that they can increase the probability of having a girl. So they believe that that probability would be greater than 0.5. So the probability of having a girl is greater than 50%. The opposite of that is being less than or equal to 0.5. So then what I can do is I can take this information and write two hypotheses. So this is my null hypothesis. This one is my alternative. This is a 0, this is a 1. The null hypothesis always contains the condition of equality. So in this case, there's an equal sign there. So this is my null. It has the condition of equality. The alternative contains the condition of inequality, so it doesn't have an equal sign in there. Something has changed, something is different. Just like previously, we would check our conditions like we had before. I'll go over these conditions specifically when we go through each test, but for the most part everything is still going to be the same or very similar. The third step, what we do is we find the probability of getting at least 0.56. To do this, what we first do is we convert this value, this 0.56, this p-hat of 0.56, into a z-score. So to do this, and this is called your test statistic. So to do that, the generic form, it's the statistic, which in this case is p-hat, minus the parameter, which is p, divided by the square root of the standard deviation of the statistic. So if I'm talking about p-hat, it's p times q divided by n. So for this particular problem, my p-hat is 0.56, my p is 0.5, p is 0.5, q is 0.5, and my n is 100. And I use p and q here. I don't mean to say p-hat and q-hat. In this scenario today, I believe I know what p is equal to. So I'm going to use that. I'm not trying to estimate it here. I have some knowledge. I believe I know that it's equal to 0.5. So I do that math there, I get 1.2. So then to find the probability of getting at least 0.56, so this was 0, so 1.5, so 1.2 is right here. I can do my normal CDF. So I do 1.2, positive infinity. This is my standard normal curve here, so I'd have a mean of 0 and a standard deviation of 1. And I type that into my calculator, I get 0.115. So this is called my p-value, which is the probability of getting your sample result if the null hypothesis was true. So my last step is my interpretation. and I'm going to write a little bit more here in a second, but in the interpretation, so the probability that we would get 0.56 with the true population proportion is equal to 0.5 is 0.115. All right, versus looking at the back of your paper. So their claim here was the same as the front. So my hypotheses would still be the same. Conditions are the same. My test statistics, so what's different here now is my p-hat is 0.88. But otherwise everything remains the same. But on the back now I get 7.6. So to find the probability of it getting at least 0.88, which I've converted to 7.6, and when I do that, I get a very small number, 1.493 times 10 to the negative 14th. So the probability that I could get 0.88 if the true population proportion is equal to 0.5 is 1.493 times 10 to the negative 14th. So it's almost zero. It's very tiny. All right, what you're doing here. So what we've done here is basically we've looked at two different scenarios, and we've seen that in these two different scenarios, 0.5 is what I believe the true population proportion to be. In one scenario, I get 0.56. This was for the Girls R Us. In the other scenario, I get 0.88. This was for the Girls Rock. And you told me initially your initial gut reaction was that 0.88 was significant and the 0.56 wasn't. Well, then what we did is we looked at some statistics here and we converted everything to a z-score. So this is 0, this was 1.2, this is 7.6. So even if we go back to what we knew about z-scores, we could say here that the 1.2 is not unusual because it's inside that range of 2, but the 7.6 is unusual because it's outside the range of 2. So just looking at the z-scores alone, I get an idea of, okay, the Girls R Us pill, nothing unusual happened here. Getting 0.56 is not unusual. So since it's not unusual, it's not unlikely for me to get 0.56, so this is probably still true. But in the Girls Rock scenario, it is unusual for me to get 0.88. So if it's so unusual, it's so unlikely that I would get 0.88. The possibility of this being true, that the proportion is actually less than or equal to 0.5, is not very likely. So then I would reject that null hypothesis. And then furthermore, all we just do is we look at it in terms of a probability. So the probability for this one we saw was 0.115. The probability of this happening was 1.493 times 10 to the negative 14, so it was practically it's just very small, almost 0. So again, even if I use my rule of 0.05, so this is not unusual, so getting this result is not that unusual if this is really the true population proportion. But getting this result is unusual if this is really the true population proportion. So since this is not unusual, what that causes me to do is I would fail to reject H naught, and I can say there is not enough evidence to conclude the Girls R Us pill increases a couple's chance of having a girl. Okay, so in this scenario, getting 0.56 is likely to occur. It's not unusual, so since it's not unusual, I would see 0.56 just alone by chance, so therefore I fail to reject that, and I still continue to believe that this is true, so I don't have enough evidence to conclude the Girls R Us pill increases the couple's chance of having a girl. However, with the other one, the Girls Rock, I get a very small probability. It is so unlikely to get 0.88. It's so unlikely to get 0.88. It has an unusual z-score. It has a very unusual probability. It's so unlikely to get 0.88 if the true proportion are actually 0.5. So therefore, I don't think that the true proportion is 0.5 anymore. So I would reject H naught, and I can say that there is enough evidence to conclude the girls' rock pill does increase a couple's chance of having a girl. All right, so two very different possibilities that occurred. Again, you could initially just looked at it. You were able to say that 0.88 was definitely further away than 0.56. However, I just didn't want to base it just on looking at it. I wanted to actually use some of the knowledge that I have about statistics and calculate some probabilities and find out what's the probability that this would occur, what's the probability that this would occur. And I did that to help me make my conclusion. There is something else that we can use called a significance level, so I just can call that alpha. That significance level, that gives me a cutoff, so it tells me at what point, at what level am I willing to tolerate things. So maybe if my significance level was 10%, I would reject anything that was less than 10%. If my significance level was 15%, then maybe in this case I still would have rejected that. It just is my level of comfort, just like we did with confidence intervals. And that is it for this section here.